Hello, so I'm Nicolas Dauban from University of Toulouse. During this summer I did an internship into the IRIT, the Laboratory of Informatics in the University of Toulouse. So I was doing an internship on music recommendation, and the team which I was working in was also working on music genre recognition. So they work on the GTSAN corpus, which is a very used corpus for music genre recognition for many years. They use the convolutional neural network on this corpus, and they had really good results. So I tried to use it also on another corpus, and I also had some good results. So that's why we participated to this challenge. But in this challenge we didn't have any temporal evolution of the features from the tracks, so we couldn't use the same network because it was a convolutional one. So in this challenge we have to do some recognition on genre subgenre, but you already know this. So we had to design a new neural network. So we tried a lot of different networks. We began with small ones, and at the beginning we used only few features, and we tried by predicting only genres, and then we began to use bigger networks and to predict genres and subgenres. During development phase, we worked only on the Discog subset. We made prediction on the others only for the final predictions, because we assumed that it was the features and the sources were quite the same. So if classifier was working well or on Discogs, we assume that it will work also well on the others. So we tried many different architectures. So we began with only few layers, and finally we add layers because we observed that by adding some layers we had better results. So this is the final network we use. There is 8 dense layers which are fully connected. Each layer has 2,000 neurons. There is a rectifier after each layer, and a sigmoid on the output. So the input size corresponds to the number of features that we use, and the input size, yes, and the output is the genres or subgenres that we predict. So we designed it with the Tiano-Lasagne framework in Python, and the optimizer used was Adam, which is used for the backpropagation. I don't know if you are if you know backpropagation, but it's used to tune the network. And the initial learning rate was to 0.0001. So we had a lot of features which was available. So we have selected them by looking at their definitions and try to select them which were looking the more relevant to do music classification. But finally, we only use the mailband for the reason that there was a large amount of data, as you may know, and so by using a lot of features, the computation time was exploding. So finally, we only use mailband because this was the first we used, and we managed to have some results with them. So as I said, to design the network and to select the features, we have to make compromise with the computation time. we maybe could have made bigger networks, or maybe use a lot more of features, but we have to deal with time. Also, we could make for one set of features and one given network, we could maybe train this a lot more, because we observed that the more we train the network, the best the result were. But we didn't really have time for this. So here is the result of the baseline. This is the best baseline, the one which were based on the popularity. And so this is our result. We only made one run, so we can see that we are always less good than the baseline, but we were better than the first baseline. This can explain, because as I said previously, we have a sigmoid on the output, and after the sigmoid we have to choose a threshold and validate and choose the prediction that are beyond this threshold. And at the beginning the threshold was too high, so for a lot of tracks there were no prediction, and the rules of the challenge were to make at least one prediction per track. So we had to add one condition. It was to select the track with a higher probability in case of no one were going beyond the threshold. So how can we improve these results? The easy answer is with more time, because we can, as I said, use bigger networks, or maybe train them more, or use more features. But we can also do some fine-tuning on the output threshold, maybe lower it, because we are lower threshold, maybe we can give more prediction, so maybe have a better scores. Maybe we can try to use some other low-level features. Finally, we only used mel bands, but maybe the bark bands, as example, would have gave better results. We don't know. We should maybe have used some batch normalization or residual blocks. We have seen that GKU has used batch normalization because it was one of the key. Okay, so in conclusion, that was a really challenging task, but really interesting for me, because I'm a beginner in this domain. But it was really interesting, so thank you to the Mediaeval and organizers of the tasks. Okay, so thank you for your attention.